Yo, welcome back to the Walk YouTube channel video. Today's video we're going to be taking a look at getting better at binary search problems. So I think I'm going to segment my problems by week, something like that. So last week was 2 pointers. This week it is binary search. So let's get into the easy problem and then we'll go up to a medium problem. I hope in these videos eventually I can do the hard problems and then it'll be easy, medium, hard. That'd be really cool. But for now, just easy, medium. So, given a positive integer num, write a function which returns true if num is a perfect square, else false. Do not use any built-in library. Also make sure to like, subscribe, and comment your favorite thing about the video or how I can improve my code. So this is pretty simple. All we're doing is just a binary search, looking for one specific number. So let's say, oops, actually, since the constraint is 1 for the lowest value, start with 1, 2, 3. Let's say we had something like 9, up to 9, right? We had a left pointer and a right pointer. And then we'd want to find the midpoint. This is how we do a binary search. We find the midpoint, and then we can see, okay, basically, what can we infer from that midpoint? The thing we can infer, right, is that 5 squared is 25, which is greater than 9. That's the general idea, right? So this is going to be our mid minus 1. And now we can see that the mid is 2. And then 2 squared is 4, which is less than 9. So we want to bring left up to 3. So left is 3. And then we can see that this is going to be the midpoint too. Mid. So 3 squared is 9, which equals that 9 that we have there. Do one more example. Say 1, 2, 3, 4, 5, 6 for an input num of 6. Last is the input num of 9. This will do 6. Obviously we know that 6 is not a perfect square, but we want to try our algorithm right. So this is left, right, and then the midpoint would be here. Mid. So we know that 3 squared is 9, which is greater than 6. So this is going to be R, since we want to get a lower value. And then in between left and right, the midpoint will be b value 1. We know 1 squared is 1, which is less than 6. So now we say left equals to the right is also mid. 2 squared is 4. 4 is less than 6. But then we cannot increment left anymore because we want left to be less than or equal to the right. So what I'm doing here is I am just doing a loop while left is less than or equal to R. And then I'm going to use a long here, a long variable for Java, working with Java today. We want to cast along because of higher range numbers being squared. So for example, 2 to the 31 minus 1. We divide that by 2, right? Because that would be the midpoint. When we square that, that's going to be a huge number. So we just want to make it a long variable. Then we want to say if mid times mid equals num. Return true. If it's less than num, then we want to kind of bring up, right? We want a higher value, so we're going to bring the left up to mid plus 1. Otherwise, we're going to bring the right down to mid minus 1. Okay, I think that's pretty straightforward. Let's get into sum of square numbers. This one is a bit more painful. At least I think my test case will run now. Oh, I don't know how to actually run it. My button's gone down here. Yeah, I think that for some reason this bottom bar is here today. I don't know why. And I'm full screen, but well, I mean, I got a correct submission. And the idea behind this is actually a little different. This is actually an ON solution. I actually couldn't figure out how to make a O log n solution. Usually binary search is log n. But let's read the question first. Given a non-negative integer c, decide whether there are two integers a and b such that a squared plus b squared equals c. We see here that there's no, constraint that a and b have to be unique. So it could be like, if we had c equals 0, which is in the constraints, then we could say 0 and 0, and that'd be perfectly fine. So let's take a look at the code first. To the left equals 0, and r equals int math squared square root c. So let's say our c value is 100. So L equals 0, right equals 10. And in the first iteration of the loop, we can see if we compare these two numbers, then we would say 0 squared plus 10 squared equals 100, so we'd return true. That's what this says here. So int num is math.pow, so L squared plus math.pow r squared, which is equal to 100. Num is equal to c, we return true. If num is greater than c, we do r minus minus. So let's think about this for a second. Let's say we had c equals 82. So the solution to this would be 9 and 1, or 9 squared plus 1 squared. That's one solution. There may be another one, but I kind of doubt it. But anyways, so we would say L equals 0 and R equals 9. Because you're doing a math square root, which returns a float. Java, I think, or double. I think it's a double type, which we convert to an integer, which will be 9. Saying while L is less than or equal to R, I say int num equals int math.pow. So if we do that, 0 squared plus 9 squared is 81, which is less than c. So we're going to go to this third condition. Let's say L plus plus. So L equals 1. Then we'll realize that this actually converts to 82. So now, this is where I got a little confused. Because, let me bring it up. Because in theory, if you had a really big number, like c equals 26205 or something, and let's say, yeah, L equals 0, and let's say the square root of this is like, I don't know, like 120. Let's just say, for example, it's 120, right? And let's just say r squared would be like 26, I don't know, 200, something like that. So it's 5 away. So how would we increment? If we were incrementing, this would be a worst case ON solution, in theory. Or I guess this would be O of taking C as the input, square root C solution, which is just N, because this is just a variable number. So it's just C to the 1/2. So C to the 1/2. But since C can be any number, it's just going to go to N. It's going to asymptotically go to N, I believe. That makes sense. Actually, we can do a little experiment. Oops, how'd that open YouTube? How'd that still open YouTube? Got a full screen. I say Desmos, and it opens YouTube. Didn't know it was possible. If we have a C to the 1/2, that's like X to the 1/2, right? Which asymptotically goes to not N, not the same as ON, X to, or if we just said X, right? But technically, I think the actual idea is that this C to the 1/2 just gets to a different constant C. Like if I say C1, I think that's the idea, which is technically ON? I don't know. I'm not sure. I'm a bit confused. Maybe because, maybe it doesn't actually matter. And it's well, it technically is better than ON as the cases go on. But you're searching the same amount. I don't know. Whereas C gets larger and gets, the square root C technically gets larger, but honestly not by much. I think that's why it's a faster solution. So let's run through the code one more time. the left is 1, because that's the constraint. And then R is num. Oops, this is the wrong problem. This is the problem. So L equals 0, that's by the constraint. And R is the square root value. And then we're going to check until they're equal, because since these two can't be, or can be unique, or don't need to be unique, we could have like 2 squared plus 2 squared equals 8. If we had 8, the idea would be 2 and 2. And then we say, okay, the num, just a num variable, is going to be the addition of the powers. Basically trying to get this formula and see if it's equal to C. If it is, then return true. Otherwise, we're going to, if it's greater than C, we're going to decrement right. Otherwise, we're going to increment left. And I guess the main kind of betterment of this algorithm, by saying the right pointer is the square root value, is that you cut off a large percentage of the data. Like for example, if you had 100, right? L equals 0, R equals 10. So you 10 through 100, or 11, anyway, 11 through 100 is cut out, right? So I guess that's the idea, is that you're really shrinking this ON complexity. But I think it's still ON. That's what I read in the submissions tab, that someone posted something similar to this. I kind of get inspiration from there too, and thought that it was ON worst case, which I guess makes sense. If you have some huge number, like 2 to the 31 minus 1, probably makes sense. Anyways, thank you for watching this video. I hope you enjoyed this quick explanation of how to get better at Leetcode. We're talking about binary search, so we start from the easier problems, go up to the harder problems. So thank you very much for watching this video. I'll see you in the next one.